You probably didn't notice anything last night, but while you were having dinner, the sun exploded. A massive M8.1 solar flare, one of the strongest in recent weeks, hurled billions of tons of electrically charged plasma directly toward Earth. And tomorrow, December 9th, it's going to arrive here. What that means for us, and why even NASA scientists were caught off guard, I'll explain right now. The facts. On December 6th, around 6 p.m. UTC, that's early afternoon on the East Coast, instruments aboard NASA's Solar Dynamics Observatory registered an M8.1 solar flare. That's the second highest category of solar eruptions. Only X-class flares are stronger. But here's where it gets interesting. This flare came from a sunspot region that scientists call AR4299. You might remember this region from November, when it was called AR4274 and was responsible for that G4 storm that brought auroras as far south as Arizona. The sun rotates about every 27 days, so this active region traveled around the backside and has now returned, bigger and more active than before. Here's the surprise. Scientists had actually been watching a different trio of sunspots, AR4294, AR4296, and AR4298 in the southern region of the sun. Those looked far more threatening. But the sun doesn't follow our expectations. AR4299 exploded, launching what's called a full halo CME into space. That means the explosion was aimed directly at us. Have you seen any of the recent auroras? Write in the comments how far south you are and whether you were able to observe them. I'm curious to hear from you. So when exactly will this coronal mass ejection hit us? Current NOAA models say December 9th, likely during the day. That's about 60 to 72 hours after the eruption, a typical travel time for these events. Now this gets technical, but stay with me because it's important. What matters isn't just the speed of the CME, but also its magnetic orientation. If the so-called BZ component, that's the magnetic field line, points southward, it can become entangled with Earth's magnetic field and trigger a stronger storm. Preliminary data shows a southward orientation. That's not good, or rather it's excellent for aurora hunters, but problematic for satellites and power grids. NOAA uses what's called the G scale for geomagnetic storms, ranging from G1 minor to G5 extreme. For tomorrow, they're forecasting a G1 to possibly G3 storm. G3 would be classified as strong. For comparison, the Carrington event of 1859 was probably a G5, as was the Halloween storm of 2003. We're not talking about an apocalyptic scenario here, but certainly a significant space weather event. What does this mean practically? For aurora watchers, during a G3 storm, the northern lights could be visible as far south as the northern United States, Michigan, Minnesota, North Dakota, Montana, perhaps even northern New York. With a G1 or G2, they'll likely stay confined to Canada and Alaska. For technology, this is where it gets more interesting. Let me be honest with you, most people won't notice anything, but there are potential impacts. I don't want to create unnecessary panic, but I also don't want to sugarcoat this. Let's talk about the real risks. Satellites in low orbits can experience additional atmospheric drag during G3 storms. That sounds strange, drag in space, but yes, the upper atmosphere expands during such storms. Satellites have to burn more fuel to maintain their orbits. In recent years, we've seen SpaceX lose several Starlink satellites during a storm. GPS systems can be disrupted. Precision GPS applications, like those used in modern agriculture or surveying, could become less accurate. Your car navigation will probably keep working, but with a few meters of deviation. High-frequency radio is interesting for the ham radio community among you. HF communication can be affected, but sometimes, and this is fascinating, geomagnetic storms can also create exceptionally good radio conditions. It's a double-edged sword. Power grids are where it gets serious. During strong geomagnetic storms, so-called geomagnetically induced currents can form in long power lines. These can damage transformers. The most famous example, Quebec, March 19. A G5 storm knocked out Quebec's entire power grid for 9 hours. 6 million people without power in winter. But, and this is important, grid operators learned from modern grids have better protective measures, and we're probably talking about a G1 to G3 here, not G5. The likelihood of a widespread blackout is very low. Here's my question for you. How dependent are you on GPS in your daily life? And would you be prepared if the power went out for a few hours? Tell me in the comments. Now we need to talk about the 10 people on the International Space Station. We just reported on this crew, NASA astronauts Mike Fincke, Zena Cardman, Chris Williams, Johnny Kim, JAXA astronaut Kimia Yui, and 5 Russian cosmonauts. Are they in danger? The short answer is they're well protected, but they'll take precautions. The ISS has reinforced areas, mainly the Russian service module and some central sections, where the crew can retreat during intense radiation. For M-class flares resulting in a G3 storm, This usually isn't necessary, but the crew will closely monitor radiation levels. X-class flares, the really big ones, can create radiation levels that would be problematic for astronauts during spacewalks. That's why EVAs are often postponed when major storms are predicted. Here's a fascinating historical note. In August 1972, between Apollo 16 and Apollo 17, there was a massive solar storm. Had astronauts been on the moon at that time, they could have received potentially lethal radiation doses. The Apollo era was lucky. Today, with a permanently occupied ISS and planned Artemis lunar missions, space weather forecasting is more important than ever. Could you imagine being on the ISS while a solar storm is raging? Would that fascinate you or frighten you? Let me know. Let me give you the bigger picture briefly. We're in solar cycle 25, and we're in solar maximum, the phase of highest activity. Interestingly, the latest NOAA data shows that the sunspot number fell to 91.8 in November 2025, significantly below the peak of 216 in August 2024. This suggests we may have already passed the peak and are entering the declining phase, but that doesn't mean the danger is over. Historically, some of the strongest solar storms can occur during the declining phase. What we've seen in recent weeks, AR 4299 returning, multiple active regions, frequent M-class flares, this is the new normal for the next year or two. So what can you do in the next 24 to 48 hours? If you want to see the northern lights, use apps like My Aurora Forecast or visit the NOAA Space Weather Prediction Center website. The best viewing time is usually between 10 p.m. and 2 a.m. You'll need clear skies and minimal light pollution. Look north, the lights appear on the horizon as a green, sometimes reddish glow. If you want to protect your technology, back up important data, which you should be doing regularly anyway. GPS-dependent applications might be less accurate tomorrow. Ham radio operators should monitor conditions. But honestly, for most people, tomorrow will be a completely normal day, with maybe spectacular auroras as a bonus. The sun continues to surprise us. AR 4299 has shown that even regions that look harmless can suddenly awaken. I'll be monitoring the situation and keeping you updated. If something unexpected happens tomorrow, whether spectacular auroras or technical impacts, I'll bring you an update. 3 questions for you. First, will you be watching for auroras tomorrow night? Second, are you concerned about potential impacts on technology? And third, would you like me to make a more detailed video about space weather and how we can prepare for it? Let me know in the comments. And subscribe to the channel and click the bell so you don't miss tomorrow's update if the storm turns out stronger than expected. If you want more of these detailed analyses, leave a like. Until next time, stay curious, stay informed.